Hello everyone and welcome to the online virtual meetup for April with GDG Cloud Bengaluru. My name is Ransi and I am the organizer for GDG Cloud Bengaluru and also your host for the session. So for today's session, we will be covering Cloud Spanner. Cloud Spanner is Google's rapidly growing planet-scale, highly scalable, multi-region and strongly consistent relational database that customers leverage to run their mission-critical workloads. As one of the world's largest and most sophisticated distributed systems, Cloud Spanner is pushing the boundaries of what is possible in distributed computing. In this talk, we'll describe Cloud Spanner's features, discuss the customer use cases, and provide an introduction to Spanner's architecture, which includes the transaction execution and the role of TrueTime. The speaker for today is Thiago Nunes, who is a senior software engineer at Google, focusing on Cloud Spanner client libraries, tooling, and the developer experience. So without further ado, over to you, Thiago. Take it away.
Hey folks, welcome to the session. Thanks Ransi for introducing. My name is Thiago. So as Ransi mentioned, I'm senior software engineer in Google Australia based on Sydney. Today, we are also going to have Nevin Hines joining us to answer any questions that you have at the end. He's one of the leads for Cloud Spanner here. So as Ransi mentioned, Spanner is a highly scalable, global, multi-regional, strongly consistent relational database. And there's lots of words there, and we're going to try to unpack those during our presentation, right? So Spanner is one of the most advanced distributed systems out there. It's constantly pushing the boundaries of what you can do with distributed computing, right? Spanner is at core for Google, so we do use for several of our services. That Google services, we serve billions of users worldwide, and all of those are powered by Spanner, right? Here we're gonna focus on Cloud Spanner, which is the offering from Google for Spanner in GCP. Okay, so let's move on here. So let's take a look at the agenda here. So first we're going to start by talking about what is Cloud Spanner, how it differs from the other products that we offer. Then we're going to jump into some product highlights and the features that Spanner offers, as well as the trade-offs it makes. Finally, we're going to go to the use cases for our customers, how Spanner help them to build their systems. Then we're going to get a little bit more technical, and we're going to talk about the internals and architecture of Spanner. So we're going to cover splits, TrueTime, and how Spanner executes queries, so reads and writes. And we're going to end with talking about the current work and challenges for Spanner. Okay, so what is Cloud Spanner? So Spanner is part of a portfolio of GCP services. It's part of our fully managed data products that we have. So we have in-memory, non-relational, relational, and data warehouse products here. Spanner is part of our relational offering sitting next to Cloud SQL. So Cloud SQL is our managed MySQL and Postgres offering. And what is the difference between that and Spanner? Well, basically, it's scalability. So Spanner is not just a single machine or a couple of machines working together, but it can scale up to hundreds, thousands, and in some cases, tens of thousands of machines working together as a single system, right? So the ability to harness multiple machines to act as a single system is often called as horizontal scalability. And when you think about horizontal scalability, this term is often associated with NoSQL or schemaless databases, right? So what is the difference from that to Spanner? So Spanner combines horizontal scalability with relational semantics. And when we talk about relational semantics here, we're talking about schemas, ACID transactions, and SQL, right? Horizontal scalability is very important for Google. So Google has some of the largest databases out there, and these databases are powered by Spanner. So you can definitely say that Spanner was battle tested by Google. Okay, so given that, let's take a look at some of the features that Spanner offers. So at first, I'd like to say that Spanner is a fully managed service. So it's easy to configure, it's easier to deploy and to maintain. You don't have to deal with the complexities of handling distributed systems internals, right? Spanner automatically sees failures and recovers from the failures that you have. It automatically shards your data based on data size and load. And Spanner doesn't have a maintenance window. So for instance, if we're upgrading software, we don't have to bring Spanner offline. So let's see how this is made possible. So here in the right, we have a picture of an overview of Spanner's architecture. And it's very important to highlight here that we decouple storage and compute. So basically, we have a single regional configuration in this picture with 3 zones. We have our compute nodes, which are the servers serving your data. So we usually call them span servers. And in the bottom here, we have the databases. And the databases are stored in a distributed file system in Google, which is called Colossus. So this distributed file system is a highly available, redundant file system. And what this separation of concerns gives us is that when you're dealing with hundreds or thousands of machines working together, eventually those machines are gonna fail, right? So what Spanner can do when this happens, it can just reroute your request to other span servers that will handle the serving of your data, right? Next, we have that Spanner is a relational database, and this is very interesting. So Spanner offers the strongest consistency level that you can have, called strong external consistency, or strict serializability. So under this consistency level, it seems like all of your transactions were executed sequentially. So other than that, the Spanner makes sure that if a transaction is executed and completed before another transaction starts, then the client that sees the second transaction will also see the first one. So it's important to highlight here that although Spanner uses several machines to compute your transactions, they all seem to the client as they were executed sequentially, right? And under the hood, this is powered by TrueTime. So TrueTime is basically a system to give a global notion of time. It uses GPS and atomic clocks to achieve that. And it also manages an uncertainty level in the global time. And we're going to talk more about this in a few slides. Next, we have Spanner's availability. So Spanner offers 5 nines of availability, which is a very, very high availability. If you like to think in negatives, that's under 30 seconds of downtime per month, right? And here on the right, we have a picture of how can we achieve that, right? So basically, Spanner partitions your data into chunks, which we call splits. This set of splits are organized into groups, and these groups are Paxos groups. Paxos is basically a consensus algorithm that we use. So within those groups, there are leaders. The leader here are marked in blue. So the leader for the first group is in zone 3, and the leader for split 1. That's what I mean. And this leader will handle all your writes and also will handle any synchronization that you need for your reads, right? And we're going to see more about that when we talk about the life of a query in Spanner. Finally, Spanner can also have multi-regional configurations. So in this picture here, what you see is a write quorum with 3 regions in the US. So you have, region 1, 2, 3, with 2 zones in region 1, 2 zones in region 2, and 1 zone in region 3. There's also read-only replicas, which are in the Asia region and Europe region. So when you're performing a write, basically the write quorum is the one that is going to handle that, right? And for a write to succeed, it needs an acknowledgement from the majority of the machines that are participating on that write. So, for instance, in this configuration, you can have a whole region outage. Let's say region 2 goes down, and your writes are still going to succeed, right? If there are any writes that are routed to the Asia or Europe region, they are going to be rerouted to your write quorum. Now, what do you get by having the replication in Asia and Europe? Basically, they bring the data closer to your client. And in Spanner, you can have 2 types of reads. So one of them is called strong reads, where you want to read the most up-to-date data. And the second one is called stale reads, where you're okay with reading data that is at most 15 seconds old, right? So Asia and Europe region can serve probably stale reads without having to do any network hops or communication with the write quorum. So that way you're going to use less resources if you do that. Okay. So now let's take a look at some of the use cases and how our customers use Spanner. So basically, we have customers in several different areas. So we have customers in gaming, fintech, healthcare, retail, technology, media, and entertainment here. I'm going to focus on gaming because I think it's a very interesting usage of Spanner. So imagine you're launching a game. Usually you don't know if that game is going to be the next big thing or not. So one thing that you need is a database that scales, right? If you have a boom of players that come to your game on day 1 or day 2, you're going to have to be able to use a database that can scale to supply your demand. And that's something that Spanner can do, right? The second thing that is very interesting is usually you're going to have players around the world. So with the multi-regional configuration that we've seen before, Spanner can supply that demand by bringing the data closer to your players, right? And finally, if your game has some kind of payment gateway, you're going to need to have strong consistency, right? So when you're processing payments, you don't want to process double payments or miss a payment because they're usually audit processes that happen. And also you don't want to bring a bad experience to your users. So you can have that with a strong consistency from Spanner. Next, I would like to talk a little bit about the customer that I think you're very familiar with, which is ShareChat. So ShareChat uses Spanner to store user profile information and user post metadata. They migrated to Spanner from DynamoDB. And the main reason why they did that was first scalability, which they could not achieve with some limitations of scale with DynamoDB, as they mentioned here on this quote. And the second big reason was cost. So with Spanner, they could model their data as a relational, with relational semantics, which reduced the number of API calls that they had to do in the database, thus reducing their costs, which is very interesting in itself. Okay, now let's get a little bit more technical here. We're going to talk about splits, TrueTime, reads and writes, and paxes within the reads and writes. So one thing that I'd like to mention again is that Spanner is one of the most advanced distributed systems out there, right? And That's made possible by some of the building blocks that you see here. So the first one is Google's network infrastructure. The infrastructure is redundant, highly available, and provides global connectivity. So with that, network partitions are very rare, right? And this is very important for us to be able to provide the high availability that we can give. The second is TrueTime. So TrueTime is a key for providing the external strong consistency that is available in Spanner and to be able to implement the current transactional semantics that Spanner offers. Finally, what we have is the software stack itself. So we do have a custom Paxos implementation, and we also have an automatic system to reshard your data based on the size of the data and the load. Cool. So let's take a look at how data is replicated in Spanner. So here we have, again, the single region configuration that we've seen before. We're going to have 3 zones, A, B, and C. And what is important to notice here is that all your databases are going to be replicated in all the zones. So zone A, B, and C are going to have a full replica of database 1 and 2. Okay. Now let's zoom in a little bit. Basically, your tables are going to be partitioned into chunks, which we call splits. In order to do that partition, we use the primary key range of your tables. So in the example here in the right, we basically have a table with an integer primary key. Well, so the key range varies from the mid int to the max int. So minus infinity to plus infinity, as they're represented here. And in this example, we have 4 splits. So 0, 1, 2, 3. Split 0 is responsible for serving the data from minus infinity to minus 100. Split 1 from minus 99 to 3000, and so on, right? Now, this example can be extended to other data types, which are, supported by our primary key definition in Spanner. So, for instance, if you had a float as a primary key, we would do the same, just the key range would be different. And other than that, this example also serves to, multi-column primary keys. So it just gets a little bit harder to draw here, but it's basically the same thing that we do. Now let's map these splits into the single region configuration that we had before. So what we're going to have is within zones A, B, and C, we're going to have a full key coverage here. So that means that A, B, and C are going to have all the splits, right, from 0 to 3. They just appear in a different order here, and we're going to see why soon, right? So what is important to notice here is that we have, these span servers, and one split is assigned to exactly one span server, when one span server can have multiple splits, right? Now, you can have this different configuration of splits because your load might be different in the different zones that you have. So what Spanner does, it moves splits around in order to cope with your load. Okay, so in a nutshell, splits are very important concept for Spanner. They have 2 key responsibilities. So the first one is that they are at core for distributing the data across span servers. And the second one is that they are part of an automatic resharding and load balancing mechanism that we have in Spanner. So splits are not static, they're constantly on the move. For instance, if your key range on split 0 is very hot, so you're receiving lots of requests there, what Spanner will do is that it can divide that split into 2 subsplits and move them into 2 different span servers in order to cope with your load. On the other hand, if you have neighboring splits, which are receiving very little load, Spanner can merge them together into a single split, right? So the key point here is that the Spanner is not constantly splitting or creating new splits. It tries to create kind of to maintain kind of a constant load in your a constant number of splits in your database, right? And that constant can actually grow as your data grows or as your load grows, but we're not splitting forever. And the second thing I would like to highlight here is that splits are not something new to Spanner itself. Splits were a concept that were first introduced when we implemented Bigtable. So I think the Bigtable's paper came out in 2004, if I'm not mistaken. So, you know, this concept has been adopted and evolved in Spanner. We do have, you know, 16 years of expertise on writing algorithms and optimizing heuristics for splits here, right? Cool. So now that we've seen splits, let's talk a little bit about TrueTime. So TrueTime is a mechanism for synchronizing clocks across machines. And these machines can be in the same data center or in different data centers. TrueTime uses GPS and atomic clocks for that. So basically, it uses these two different technologies to cope with the failures in the other. But what is important to notice here is that even though we use GPS and atomic clocks, you still can have clock drift, right? So here in the right in this graph, we kind of have a representation of what that looks like. So the uncertainty or that clock drift starts small and increases over time. And you see here that close to the 30 seconds, what happens is that TrueTime synchronizes the clock in order to reduce that uncertainty. So that's why you see this sawtooth graph, right? The error starts small, it starts increasing with time. When there's a synchronization, it goes back down, and so on. So it's at core for TrueTime to manage and quantify this uncertainty. And the other thing that is very important at TrueTime is that it guarantees that the clock drift error is to be maintained within order of milliseconds. And when I'm talking about the order of milliseconds here, I'm talking about 1 or 2 milliseconds, right? So that's order of magnitudes better than what you can have with other network time systems. So let's take a look at how we use TrueTime. So basically, when you call TrueTime.now to get the current time, you're going to receive a time and an error. So that uncertainty or that clock drift, right? Another way to look at this is that you're going to receive an interval from T1 to T2, where TrueTime guarantees that the global time is within that interval. So how does Spanner uses TrueTime? So Spanner uses TrueTime in order to order its events. And the most important events in Spanner are transactions, right? So when you get the TrueTime time of 2 transactions, as long as the intervals don't overlap, then you're going to know which transaction completed before the other. Now, if the intervals do overlap, then you cannot draw any conclusions about which one happened before the other, right? Cool. Excuse me a second. Cool. So now that we've seen TrueTime and splits, let's try to apply these concepts into the life of a query. So here we're trying to do a strong or a consistent read. As I mentioned before, we have 2 types of reads. So we have strong reads, but you want to read the latest version of your data. And you have stale reads where you're okay with reading data which is at most 15 seconds old. Right? In this case, we want to do a strong read. So we're reading key 1 through 3 from my table here. So what happens first is that the client makes a request to Spanner. Spanner will see this request, will analyze the key that it wants to read, and then it will identify the split that contains, that is responsible for that key, right? And then it will reroute the request to a span server that contains a split, usually within the zone that is closest to the client. The second thing that will happen is that if the span server that was requested was not the leader, right? Then it will need to talk to the leader to see if it has the latest data. The leader then will reply with the TrueTime time of that data. And then here the span server or split two can do one of two things. So the first thing that it can do is, if it already has the latest data, then it can just reply back to the client saying, here's your data. If it doesn't have, then it has to wait for the leader to update its data before it can reply to the client. Cool. So the next type of read, as I mentioned before, that we have are stale reads. So here we're going to do the same thing. We want to read key 1 to 3 from my table, but we're doing a stale read. So we're okay with getting data which is at most 15 seconds old. So the request starts as before. The request is made to Spanner. Spanner identifies the split that contains a key, routes the request to the closest zone to the client, and then here's where it starts to be a little bit different than the strong read that we had before. So the split will see if it has a data which is at most 15 seconds old. And if it already has that data, it can directly reply to the client without having to do a round trip to the leader. So that's why, you know, when you're doing stale reads, you can consume way less resources than doing strong reads here. Now, if the split 2 didn't have data which was at most 15 seconds old, then it would have to go to the leader as we've seen before. So the process would have been the same. Okay. So next, let's see how a write works. So a write is always handled by the leader. So when a client wants to do a write, Spanner will identify the split where that write will go to, and then it will route the request to the leader of that Paxos group. In this case here, it's the one in zone 2. The first thing that that span server will do is it will acquire logs and then ask the other splits in its Paxos group to apply the write. Once it receives an acknowledgement from the majority of the group, including itself, it will consider the group the write successful. It will release the logs and it will send back a success back to the client. Now, one thing that is important to notice here is that I mentioned that the acknowledgement only needs to come from the majority of the participants, right? So in this example, for instance, zone 1 could have gone down and your writes would still succeed because zone 2 and zone 3 would have given acknowledgements. Now, if the leader zone went down, let's say zone 2 went down, then a new leader election would have to happen between zone 1 and zone 3, and then the writes could resume then. Cool. So, you know, given that, I want to talk a little bit about the current work that we're doing with Spanner and some of the challenges. So we're constantly developing new features at a cutting edge of databases and distributed computing. We have recently launched point-in-time recovery, where you can recover versions of your database which are 7 days old, up to 7 days old. We're also starting to implement CDC, so change data capture for Spanner. We're constantly working on developer productivity, so we want to make developing with Spanner a very good process for any software developer. So we have provided ORM support already for Hibernate, Spring Data. We are doing with Django now. I think it's on beta, and we're working on other object relational mapping frameworks as well. We also do have migration tools. So if you want to evaluate Spanner, Harbor Bridge is one of them, where you can basically plug in your schema from your MySQL or Postgres database, and Harbor Bridge will generate a similar schema in Spanner for you to test it out. Other than that, we do have a very vibrant open source community. So we did have passionate customers who have open sourced their tools for other Spanner developers, and we're accepting contributions from around the globe. So if you're interested, there's a link here for the Cloud Spanner ecosystem on GitHub, and you can take a look at the projects that we have there and possibly contribute to one of them. And finally, what I wanted to say was that Google Cloud has a growing presence in Bengaluru. Even Cloud Spanner now is starting a team in Bengaluru, and we're hiring. So here's a link for a LinkedIn position that we have open, but you can also talk to me in LinkedIn, and we can see what can we do from there. Yeah, so ping me up if you're interested in working in Spanner. And that's it. So if you have any questions, feel free to send them our way. Thanks.
Yeah, thank you, Thiago. This was like a very great insight, sort of like a 5,000 feet overview of Spanner, and you also went deep dive into some of the technical levels at some of the important technical advancements. So thank you. So we've actually got a few questions. So before that, let me add Nevin to the screen. Hey, hi, Nevin. Welcome.
Hi, Ransi. Thank you.
Thank you.
So, yeah, so we have some questions. So let me pop that up on the screen. Yes, first one is, what do you mean by sharding?
Yeah, that's a good question. So whenever you have your data, your database there, what we do is we split that data into several chunks, and as I mentioned, these chunks are called splits, right? And that's what we mean by sharding. So you're going to have different shards in your database, and they're going to be handled by different span servers. Nevin, I don't know if you have anything to add there.
Yeah, absolutely. Just to make a comment that sharding is a pretty common concept in databases. So very common to use with, let's say, MySQL or Postgres database. And one of the differences with Spanner is that Spanner manages the sharding automatically. So, it's something we use for load balancing and for mapping, huge databases across many span servers. And that this is something that this sharding is basically managed automatically by Spanner, and it evolves based on your load. So contrast that with many sharding mechanisms that are used in more traditional databases, let's say MySQL, Postgres, where sharding is often very static. And so if your load or your database grows and you need to change the sharding, then this can become a really complicated operational aspect of running your system. So resharding can be really quite complex and expensive and hard to manage. So yeah, just wanted to emphasize that on the Spanner side, this is something that automatically happens as part of the implementation. It's not something that you as a user need to worry about. It's something that Spanner takes care of automatically.
Cool, thanks. The other question is, what do you mean by Paxos?
Yeah, that's a good question. So Paxos is basically distributed consensus algorithm that is used in Spanner. So we definitely use that in order to apply two-phase commit and also elect leaders within groups. So you've seen that when we created several splits in different zones, we had one leader that was elected, and that's using the Paxos algorithm. So in distributed computing, leader election is kind of a classic problem, and Paxos is one of the implementations that you have out there. There's another one which is very famous as well called Raft, and that's used in etcd tool in Linux, right?
Okay. So the next one is more of one of a question and the other one is a comment. What is the cost efficiency while using Spanner? And the comment is there are some reports that indicate that Spanner is more expensive than other alternatives.
Yeah, that's a good question. So as you've seen in the examples of one of our customers, for instance, ShareChat, you've seen that they actually use Spanner to reduce costs instead of increase the cost there. So what is very important to notice here is that when you use, for instance, NoSQL databases, you're going to have to denormalize your data in order to do that, right? And that usually reflects by having your application having to do multiple requests to the database to get the data that you need, or you have to make other trade-offs in your application elsewhere. So what you get with Spanner is that relational model out of the box. The other thing that you get is that Spanner is a fully managed service, right? So you don't have to deal with maintaining your network or handling the failures or anything else. Like that's basically done for you by us. So that's included in the price.
Navin, do you want to add anything more?
Yeah, I think the only thing I would add to what Thiago said is it's really important to focus on total cost of ownership. And we strongly believe that Spanner is very price competitive. We have a lot of customers who have seen that and have actually seen cost savings. So, what you pay for Spanner includes everything, including, all the licensing, all the upgrades, everything's included as a managed service, and including replicas and managing replicas. So, it's basically a total package. And even though the sort of introductory sticker price you might see for other systems might appear lower, once you add in all of the components and actually figure out total cost of ownership, that's really the thing to focus on.
Okay, great. The other one is, was Raft considered instead of Paxos, and what are the final trade-offs in choosing Paxos versus Raft?
Yeah, I don't know exactly if we consider Raft. I think Raft came after Paxos, some years after. So I think that we were already done with the implementation of Paxos when Raft came out. I know that's a very interesting alternative to Paxos, but we did spend a lot of time customizing our Paxos algorithm and optimizing that. So there's no reason for us to change at the moment.
Okay. The other one is sort of like a comment to me that please share the backend engineering opening link. So I assume that you would be sharing the deck to me and then I can post it to the community, right?
Yes, yeah, that's correct.
Okay, yeah, thank you. We have another one, sharding, is it static or dynamic? And if it is dynamic, what are the sequences of rule or steps?
So sharding, as Nevin mentioned here, is dynamic, right? We don't want to do static sharding because it's such a pain to manage shards. I think that's one of the main reasons why we don't, why you have problems, start having problems with, MySQL or Postgres. When you have to do schema migrations becomes very difficult. Maintaining the database becomes very difficult. Creating this becomes very difficult, and so on. So the second question is, what are the sequence or rule or step? I think I don't understand your question here.
I think its question is about how is the sharding set up?
Okay.
And internally, Spanner has several heuristics. I mean, essentially, it has an algorithm for dynamically managing the sharding, the what we call splits. So very briefly, there are algorithms to take a split and to split it into smaller splits. So split a split. I know that's kind of confusing terminology here, but view this as a sequence, a chunk of keys in the key range. And when that either gets too big because there's too much data in it, so you've just got too much data in that split, or there's too much load. So the CPU usage within that particular split, within that particular partition becomes too high. Either of those will trigger an algorithm which basically cuts this into pieces, so that now you finish up with smaller splits. Now, if you keep cutting, then you keep finishing up with many, many splits. And so over time, the number of splits would just keep increasing. So there has to be another algorithm that stops the arbitrary increase in number of splits. And it's essentially a merging algorithm. And it will look at neighboring splits and say, hey, it looks like these two splits are fairly small and they haven't seen much load over the last few days. So let's merge them back together again. And the reason for doing this is there's an overhead in each split. There's some memory cost, some management cost. And so, we don't just want to arbitrarily increase the number of splits. We don't just want to carve it up into smaller and smaller pieces. So, we're trying to maintain an equilibrium. We want splits to be of reasonable size, so not too big, because if you have really big splits, then you'll run into problems with compaction. You might run into problems with availability. You might run into problems that there's just too much data that can potentially be accessed on a span server for this large split. So we try to keep them into small, manageable pieces. And the other aspect of this is that we want to manage the load, the CPU load. So it's important to have manageable pieces that we can move from one span server to another and spread the load out. So those are essentially the heuristics that are going on. And, it's a dynamic process. If you take a database and add a lot more load, then you'd expect the splits to grow. If you take a database and inject a lot of new data, you'll expect the number of splits to grow because there's simply the amount of data is growing. So if your database is growing over time because you've got more data, then you're going to expect the number of splits to be increasing.
Great, excellent insights. Thank you, Nevin and Thiago. We have one more question. Yeah. When we discussed about strong consistency, you had mentioned about strict serializability, which is more of an isolation construct. Wouldn't linearizability be the right construct for strong consistency?
Yeah, so basically, if you look at the definition of strict serializability, you're going to see that it's a combination of linearizability with serializability. And that's what Spanner can grant you. So I think it's sometimes a kind of an overloaded term, and you can get confused there. But that's why we call it external consistency. But if you look at the, what was it called, the Jepson definition of consistency or isolation levels that you have, you're going to see that Spanner has the highest one.
Okay. Other one is, will the split storing of the row be hot, and how Spanner handles reducing the hotspot or steps to avoid the hotspot?
Yeah, so we do have, as Nevin mentioned, this automatic system for splitting key ranges based on load, which is very interesting. I haven't seen that in other systems, but you still can have hot keys, right? And the ways that you deal with hotkeys is you can have read-only replicas in a multi-regional configuration or a single region configuration. And the other thing you can do is we do have, best practices to avoid some of the pitfalls that you see with hotkeys. So in the final slide of the presentation, there's actually some links of Cloud Spanner and Cloud Spanner tutorials, and you're going to see some of the recommendations that we have to avoid that.
Great. Yeah, I guess that's all with the questions that we had. Yeah, so thank you again, Thiago and Nevin. So great to host you, and we had some wonderful questions coming in. So thank you all for tuning in as well. So until the next time, stay home, stay safe and see you later. Thank you, everyone. And thank you, Nevin and
See
Pierre.
you. Thank you very much for having
Thank
us.
you.
Bye-bye.